In this lecture, we begin a new chapter, namely chapter 14. This chapter is very important. It pertains to calculus of functions of more than one variable, means function of two or more variables. You are familiar with calculus of function of one real variable, y equal to fx. Okay, here you will learn calculus of function of two real variables, z equal to fxy. Here x is one independent variable, here xy both are independent variables. Okay, so before I begin the calculus or I discuss the calculus of z equal to fxy, let me ask you something. What are real numbers? I believe you are familiar with the natural numbers or counting numbers. N is the set of natural numbers 1 to 3 and so on. Z is the set of integers 0 plus minus 1 plus minus 2 and so on. Q is the set of rational numbers, means numbers of the form p by q, where p, q are integers, q is non-zero. I is the set of irrational numbers, means the numbers which cannot be written in the form p upon q for all pq belonging to z. Do you know some examples of irrational numbers? Root 2, 1.414, etc., and so on. Then pi is another irrational number, 3.14 and so on. E, the exponential number, 2.738, 1 point or 2.738. Okay, it's 2.738. Do you know the difference between rational and irrational numbers when these are represented in decimal form? See, 1 by 2 is 0.5. In decimal form, this rational number, the decimal form terminates after one digit. 1 by 3 decimal form does not terminate, 3 repeats again and again. You can write it like this. 1 by 7 in decimal form can be written as 0.142857. After that, the same group of digits repeats. You can check it. So these are three situations when you have a rational number. Either the decimal form terminates, or a digit repeats, or a group of digit repeats. But in case of a rational number, the decimal form is neither terminating nor repeating. So you should know this difference between rational and irrational numbers. What are real numbers? Q union I. If you mix rational and irrational numbers together, you get the set of real numbers. You are familiar with this number line where the integers are directly visible. You label them, fractions are in between. This number line, or you can say real number line, is fully packed with the real numbers. Okay, so these are real numbers. Now, one side I will keep the concepts of a function of one real variable, real valued function of one real variable x. Other side, for comparison purpose, I will define the related concept for a function of two variables. So first, what is a function of one variable? Recall from the calculus that you've done in 11th and 12th standard. F is a function from a set X to a set Y. How you define it? If F is a rule that assigns to each value X in X a unique value Y in Y, or diagrammatically can show it like this. F is a rule that assigns a unique value Y in Y to each value X belonging to X. You denote this Y value by Fx. Okay, so if this happens, then F is a function from the set X to the set Y. You call the set X as domain of X, Y as codomain, set of images you call the range of F. So what is domain of the function F? Capital X. Range of the function F. Collection of all Fx where X belongs to the domain of the function. And one more thing we define that is useful, graph of the function Fx. Graph means collection of the points x comma fx where x belongs to the domain of the function. Okay, so domain, range and graph. And you can plot the graph in xy plane. Means you can represent this set geometrically in the xy plane. So you know these things already. Now let's see how we define a function of two variables. F is a function from x cross y to z. X cross y, you know, set of ordered pairs x comma y where x belongs to x, y belongs to y. So if F is a rule by which to each value xy in x cross y can be assigned, or you can say if F is a rule that assigns to each value xy of x cross y a unique value z in z, then F is a function from x cross y to z. Similar definition, okay? And we denote this z by fxy. So what is domain this time? The collection of ordered pairs, or I can simply write x cross y. What is x cross y? Collection of the ordered pairs x comma y where x belongs to x, y belongs to y. What is range of f? Set of all images corresponding to the points in the domain, means collection of all fxy where xy belong to the domain of the function. Same way you can compare. And graph. Graph is the collection of the points x comma y comma fxy where xy belongs to the domain of the function. You can compare the definitions here and see what is the difference. In this case, domain lies on x-axis, isn't it? X is the set of real numbers, so you can say it lies on x-axis. But in this case, domain is carrying the collection of ordered pairs, and ordered pairs lie in xy plane. It means domain of the function of two variables lies in xy plane. Okay, there is a difference in the graph also. Here, this graph can be represented geometrically in the xy plane, but here the graph can be represented in xyz space. So there is difference. Okay, let's see some examples to understand these definitions. Let's first see an example for a function of one variable. Consider fx equal to root 1 minus x square. Can you tell me its domain, range, and graph? Domain of this function is it is defined in which interval? Minus 1 to 1? Then write this simply as the closed interval minus 1 to 1, because you get a real value when x square is less than or equal to 1. This gives you this interval where x lies. Range of f, can you think? Minimum value is 0. You will get all real numbers from 0 to 1. And graph of this function, as usual in the definition, x comma fx, or you can write fx expression root 1 minus x square, where x belongs to the domain, means minus 1 to 1. Do you know the geometry of this graph? Can you represent it geometrically? Yes. If you assume it y, you can recall that it is semicircle, minus 1 to 1, maximum value 1, x-axis, y-axis. So for this function, domain lies on x-axis, the closed interval minus 1 to 1. Okay, and this is the graph, which is geometrically is the semicircle, as shown here. Range is 0 to 1. So this thing you understand very well. Now I write this function, square root of 1 minus x square minus y square. This is something new for you. Think, what is the domain? Collection of all xy, where x square plus y square is less than or equal to 1. Here, collection of all x where x square is less than or equal to 1. Okay, under this condition only, the expression under the square root sign remains 0 or greater than 0. Okay, so this set is the domain. What is the range of this? Minimum value 0 and maximum value 1, and intermediate value you will get. Okay, this is the range. Graph, you can write it like this: x comma y comma square root of 1 minus x square minus y square. Collection of all these points in space where x, y belong to the domain of the function, as defined here. Now, can you displace this graph geometrically? Yes. How? This time this is the domain of the function. See it carefully. Collection of all xy where x square plus y square less than or equal to 1. So less than or equal to 1 means what? X square plus y square less than or equal to 1 means the region inside and on this unit circle. X square plus y square equal to 1 is this circle. Less than less than 1 means all points inside it. This is the domain of this function. Okay, domain you have shown graphically. Here the domain is the interval minus 1 to 1 that you have shown on x-axis. In this case, domain lies in the xy plane. It is a region. What is plot of this? Means graph. What is the graph of this function? Domain you have shown. Let's assume it is z. If you simplify it, means square both sides, you can think that it is actually x square plus y square plus z square equal to 1. That you know is a sphere of unit radius centered at origin. So only positive part means the hemisphere above xy plane. Hemisphere above xy plane. Okay. So now observe the differences. Here the domain lies on x-axis, the closed interval -1 to 1. Here the domain is the unit circular disk. Unit circular disk. This whole region x square plus y square less than equal to 1. Here graph is a curve in xy plane. Here graph is a surface. Note this point. Graph of a function of two variables is a surface in space. And see this. If you project this semicircle on x-axis, you exactly get its domain. Means exactly get the domain of the function fx, this function. If you project this hemisphere on xy plane, what do you get? This unit circular disk. Okay, so observe these differences. These are important. Now let me write one more function that would be interesting for you. Fx equal to this, fxy equal to this. Now fxyz, function of three variables. Can you write its domain? Can you write its domain? Collection of all x, y, z, where x square plus y square plus z square should be less than equal to 1. Range also you can think easily. The closed interval 0 to 1, minimum value, maximum value, and all intermediate points will get. And graph also you can write x comma y comma square root of this, where x, y, z belong to the domain. Now think about its geometry. That is the difference you will see among these three cases. What is the domain of this function? If you want to display domain first, just like we displayed the domain first, this unit circular disk. Here, what is the domain? It is the unit spherical region. Okay, the region is like this in 3D. The unit sphere centered at origin, radius 1, this whole region. This unit spherical region is the domain of the function. How can you display the graph of this function? For graph, there are three coordinates x, y, z for the domain and one more related to the range. Okay, so how to display it? Where x, y, z belong to the domain of the function. How to display it? You need a four-dimensional space. Can you access four dimensions? No. We have the access to three dimensions only. Though you might have heard in general relativity and special relativity, there are four dimensions. There is time dimension with the space. But that is a different story. Here we are talking about the geometry of the function. It means we cannot display a function of three variables geometrically. We can only display its domain in the 3D space. Okay, so geometrically function of three variables is not interesting. But it doesn't mean that the function of two or more means three or more variables are not interesting. These are having many applications, you will see later. Okay, but it has no geometry, of course. You cannot display it geometrically. So you understood these three cases. What happens when you go from x, xy, and then xyz? It means as you increase the number of variables in the function, how the geometry changes. Notice this carefully. Okay, so you have understood how to define functions for one variable, two variable, and more than two variable also. Now, the next thing that I want to discuss is neighborhood. This is very important. Shortcut I will use NBD. The concept of neighborhood is very important to understand the concept of limit, continuity, etc. Okay, so see what is neighborhood. It's very simple. First, see in one variable. Suppose x naught is a real number. Its neighborhood is any interval, any open interval x naught minus delta to x naught plus delta. This is neighborhood of x0. Here I have taken at the center, but it's not necessary. If I don't take the center, still it is neighborhood. Okay, think it like this. 1, 2, 4. Okay, so there are points 2, 3 inside this interval. There is 2.5 also. So the open interval 1 to 4 is neighborhood of 2.5. It is neighborhood of 2, 3, and in fact all the points inside this interval. The idea is that neighborhood means a continuous collection around the point. A continuous collection of points around the given point constitutes its neighborhood. Okay, so this open interval is what? A continuous collection of points around x0. So as I said, it need not to be at the center. Okay, it can be anywhere in this interval. Main idea is that there should be continuous collection to the left as well as right. So 1 to 4 is neighborhood of 2.5 as well as 2 as well as 3. If you, in fact, it is neighborhood of any point inside this interval. So continuous collection of points without boundary. Okay, keep it open. This interval defines neighborhood of x0. Same way, in case of two variables, you have a point x0, y0 in xy plane. How to define its neighborhood? Any region, because now you are not restricted to x-axis, you are in xy plane. So you can consider any continuous collection of points around x0, y0 for its neighborhood. So what can you consider as a convenient neighborhood? Say we consider a circular region around it of radius delta. So how can I write it? X minus x naught whole square plus y minus y0 whole square root less than delta. So this is circular neighborhood for the point x0, y0. I could construct a square neighborhood also. I can take any mathematical shape, any convenient mathematical shape or mathematical relation that represents a region around the point. I could choose this also. What is this? These together represent the square neighborhood, right? These two lines are x naught minus delta 2, x naught plus delta. These two lines are y naught minus delta 2, y naught plus delta. So common region is the square neighborhood of the point x0, y0. Hope you understand this. The main idea is that it is a continuous collection of points around the point, around the given point for which you want to construct the neighborhood. In one dimension, this could be written like this: x minus x0 less than delta. It means it is the collection of those values of x for which the distance from x naught is less than delta. Okay, so it is just extension of that one in two dimensions. Same way you can think neighborhood for a point in three dimensions. Now you are in space, so which kind of neighborhood you can construct? Take one more term here, z minus z naught whole square. Do you understand what is it geometrically? If the point is in space, then it is a then it is a sphere, or you can say a region like this in 3D around the point x0, y0, z0. This is spherical neighborhood of the point x0, y0, z0, this one. Okay, this whole expression less than delta. You could construct this neighborhood also, add one more inequality here. Then this is cuboidal neighborhood. Okay, so you understand this. Okay, mainly we will be discussing function of two variables. So let's focus on these. So again, I repeat, neighborhood of a point x0 on x-axis is what? The open interval carrying this point. You can keep it at center also, no problem, right? And neighborhood for a point x0, y0 that is lying in xy plane, you can choose either the square neighborhood, you could choose rectangular neighborhood also, delta 1, delta 2. Okay, you understand that idea. Fine. So you can choose square neighborhood, you can choose uh, this circular neighborhood, Okay, so by this, hope you understand the idea of neighborhood. Neighborhood of a point is a continuous collection of the points around that point. That is the main idea. In this case, continuous collection, you can consider an open interval. And in this case, you can consider open circle. When I'm using the word open means without boundary. Okay. In this case, there are only 2 points on the boundary, but in this case, there are infinitely many. All right, so you understand the idea of neighborhood. We will use it. Okay. Before I move further, let me tell you some more terms which are common. One is interior point, then boundary point, and other is exterior point. What are these? Through example, you can understand it easily. Interior point means a point of which at least one neighborhood lies in the given set. Okay, think it like this. I'm choosing this interval 1 to 4. I'm considering a point inside it. Now tell me, 2 is interior point, boundary point, or exterior point? It is interior point. Interior point means you can construct a neighborhood. However small, it doesn't matter. You should be able to get at least one neighborhood inside the given set. Here set, I'm choosing this closed interval. So 2 is the interior point of S. What is 1? Boundary point. Because whatever neighborhood you can, okay, before that, let me tell you exterior point also, then it will be easier to understand the boundary point. Exterior point means, say, for example, I consider 5. I can construct a neighborhood, an open interval around 5 that completely lies outside this interval. So 5 is an exterior point. What is boundary point? Boundary point is a point whose every neighborhood carries interior points as well as exterior points. Such points are boundary points. Okay. So here 4 is a boundary point, 1 is also a boundary point. This is the case of 1D. Now see what happens in case of two variables. Consider this unit circle. If I ask you, let's say the radius is 1. If I ask you what is this point or this circle, my set here is collection of all xy such that x square plus y square less than equal to 1. So I'm considering all the points inside as well as on the boundary. This is my set. Now I'm asking you what is 1 for this set? Boundary point, interior point, or exterior point? is clearly boundary point, because whatever neighborhood you construct around this point, it will carry interior points as well as exterior points. Okay, this point is 1 comma 0. All right. If I ask you what is 1 1 for this point, what will you say? 1 1. Is it inside or outside? It is outside, because 1 plus 1, 2. 2 is not less than equal to 1. So you can construct a neighborhood around it that completely lies outside this circle. So it is exterior point. If I consider say 0 0, that is the center of the circle, is it exterior or boundary or interior point? It is interior point, because you can construct a neighborhood around it that lies inside the circle. So idea is neighborhood in each case. Interior point, the neighborhood of the point, you can find a neighborhood of the point that completely lies inside the set. Exterior point means the neighborhood lies completely, you are able to find a neighborhood that completely lies outside the set. Boundary point means whatever neighborhood you construct, it carries points inside the set as well as outside the set. I hope you understand. Same way you can think in 3D. All right. Now a very important concept, that is of limit. Limit is very fundamental in calculus. You should know the real meaning of limit. What you have learned in 12th standard is not sufficient. See, what is limit? What is the meaning of x approaching to x0? What you have learned in your 12th standard? You have learned that x is not equal to x0, but x is very close to x0. If this happens, x tends to x0. But what is the meaning of that very close? Hmm? What is the meaning of that very close? Let me tell you the real definition now. X tends to x0 means x not equal to x naught takes infinitely many values in each neighborhood of x0. If x is a real variable not equal to x naught takes infinitely many values in each neighborhood of x0, then we say that x tends to x0. Now understand, what does it mean? This is x naught. According to this statement, you can choose your neighborhood as small as you like. X naught minus delta to x naught plus delta. Now you choose delta very, very small. So this gets smaller and smaller, smaller and smaller. But according to this statement, each neighborhood, however small it is, carries how many values of x? Infinitely many values of x. That's why it is very close to x0. That is the meaning of closeness. Same definition you can write for xy going to x0, y0. If the pair of variables xy not equal to x0, y0 takes infinitely many values in each neighborhood of x0, y0. Now what is neighborhood? An open region in xy plane around x0, y0. So in each neighborhood, however small it is, there are infinitely many values of xy. That means xy is really close to x0, y0. Okay, that is the meaning of close to. Okay, same way you can define for three variables if you like. Do you understand this thing now? The meaning of x tending to x0? Think over it again, what I've written here. X tending to x0 means x is a real variable that takes infinitely many values in each neighborhood of x0. Each neighborhood means you can choose however small neighborhood you like. Whatever is the size of this neighborhood, length of this interval. You can choose very, very small. Still, x is having infinitely many values in that neighborhood. Infinitely many values even in a very small neighborhood. That means x is close to x0. Same thing happens here. Now see the difference between the two. Here, x can approach to x0 from left side as well as right side. You call left hand limit right hand limit. You give these notations. But here, x can approach to x0 in how many ways? Hmm? Infinitely many ways. So in case of two variables, there is no concept of left hand limit and right hand limit. Okay? xy can approach to x0, y0 in infinitely many ways. You should know it. Now, let me define the limit of the function as x tends to x0. You are familiar with this expression and you also know how you define it. You define it by saying that in your 12th standard, as x tends to x0, fx tends to L. But now you will see the classical definition of this limit. What is that? It reads like this: given any epsilon positive, there exists delta positive such that, or given any epsilon positive, there exists delta depending on epsilon such that 0 less than mod x minus x naught less than delta implies mod fx minus L is less than epsilon. Okay, suppose fx is defined in some neighborhood of x0 except possible at x0. That's why we put 0 less than. Okay. Limit of a function may exist at a point even if the function is not defined there. So you can skip x0 in the definition. So what is the definition? Given any epsilon positive, there exists delta positive such that whenever x belongs to which interval? X naught minus delta to x naught plus delta, excluding x naught, of course. Whenever x belongs to this interval, the corresponding values of fx should lie in which interval? L minus epsilon to L plus epsilon. You can read this statement like this. Writing like this, you can understand it geometrically. Suppose this is your curve. This point corresponds to x0. And fx value is L here. Now given any epsilon positive means epsilon neighborhood of L. In fact, this is epsilon neighborhood of L. Okay, the open interval carrying L. L minus epsilon to L plus epsilon. So there exists delta positive such that the part of the curve in the interval x naught minus delta to x naught plus delta lies in this horizontal strip. And think it like this. X belongs to this interval. This part is clear. X lies in this interval. May not be equal to x0. Corresponding to these values of x, the values of fx lie in which interval? L minus epsilon to L plus epsilon. So these are fx values, right? So the corresponding part of the curve lies in this horizontal strip. The part of the curve corresponding to x belonging to this interval lies in this horizontal strip. You can say like that. okay, lies in this horizontal strip. So geometrically you can understand like this, but it has a very simple meaning mathematically. It carries to the definition that you learned in your 12th standard. Actually, this delta depends on epsilon. Okay, I will do an example, you'll understand. So what happens is you choose epsilon because this is given epsilon positive. It means epsilon is at your discretion. So as epsilon goes to 0, this delta goes to 0. That says the same thing. As x tends to x0, fx goes to L. Okay, I have explained all these things for your understanding. But now let's do one example to understand this epsilon delta definition for one variable. Then I will define limit for a function of two variables and do one example. So let's take this example. Show that limit of the function 2x plus 1 as x tends to 1 is 3. By direct substitution, you know the answer is correct, 3. But let's prove it using epsilon delta. For a given epsilon, how we get a delta depending on epsilon. So let's start with mod fx minus L. What is fx here? 2x plus 1. L is 3. Let's solve it further. We get 2 times mod x minus 1. This can be less than epsilon if mod x minus 1 is less than epsilon by 2. Am I right? If mod x minus 1 is less than epsilon by 2, this expression is less than epsilon. So let us choose epsilon by 2 as delta. So I have established this condition that mod of fx minus L is less than epsilon when mod x minus x naught is less than delta. Here x naught is 1. It means limit of this function as x tends to 1 is 3 because it satisfies this classical definition of limit. And you can see here clearly as epsilon goes to 0, delta goes to 0. So that's what I was trying to tell you here. Okay, so for a given epsilon positive, you can find delta using this approach. You have to make some manipulations to get to this definition of limit. Okay. So using epsilon delta, you can solve the limit problems. Now see the definition for a function of two variables. Rather, you can write yourself. Limit xy going to x0 y0 fxy is L. How to define it? Write the same sentence. Given epsilon positive, there exists delta positive such that here neighborhood, the meaning of neighborhood changes, you know. In case of two variables, you need to write one more inequality, comma, 0 less than mod x minus x naught less than delta, comma, 0 less than mod y minus y0 less than delta implies mod fxy minus L is less than epsilon. Geometrically also you can understand. This time what is the geometry? There I explained that in delta neighborhood of the x, the corresponding curve lies in the horizontal strip. There L minus epsilon to L plus epsilon are lines parallel to x-axis. But here, what are these L minus epsilon to L plus epsilon? This you know, this is square neighborhood that I have considered. L minus epsilon, these are z values now, not y values. So these are planes parallel to the xy plane. So corresponding to this neighborhood of x0, y0, the part of the surface, because fxy is not a curve now, it is a surface. The part of the surface lies between these two planes. Okay, you can think like that. But again, the idea is same. The delta depends on epsilon such that when epsilon goes to 0, delta goes to 0. That says the same thing. That as xy tend to x0, y0, fxy tends to L. Let's do a problem. To understand this, how to apply in a given problem, take a simple example. Prove that limit of 2x plus 2y plus 1 is 5 as xy goes to 1, 1. By direct substitution, it is clear that 2 plus 2 plus 1 is 5. But you have to prove it using epsilon delta definition. So do this also the same way. Start with mod of fxy minus L. Simplify it. You get 2x plus 2y plus 1 minus 5. This you can write as 2 times x minus 2 plus 2 times y minus 2. Because it is minus 4, so I adjusted the terms. By triangle inequality, you know that mod x plus y is less than equal to mod x plus mod y. So you can write it 2 times mod x minus 2 less than equal to 2 times mod x minus 2 plus 2 times mod y minus 2. Now I want this thing less than epsilon. How can I say that? I can say this by writing that mod x minus 2 is less than epsilon by 4, mod y minus 2 is less than epsilon by 4. When mod x minus 2 is less than epsilon by 4, mod y minus 2 less than epsilon by 4, then this whole expression is less than epsilon. That's correct. Call this as delta. So you have established these conditions. You can check. Here x0, no, 2 I have taken out, so it is 1 everywhere. It is 1 everywhere. Okay. So what is x0, y0 here? 1 and 1. Delta is epsilon by 4. And this fxy is your 2x plus 2y plus 1. So you can check that the conditions for the limit are, means this definition of limit is satisfied here. So you can say that limit of this function as xy goes to 1, 1 is 5. Okay, so this way you can apply the epsilon delta definition, but it's not necessary you do a problem by epsilon delta. Okay, there are other ways also to get the answer for the limit. Let's see some other methods. In epsilon delta also there is no problem. You start with this thing and do some manipulations to satisfy the definition of the limit. That's it. But in this case, of course, you should know the answer of the limit in advance. Only then you can simplify like this. So what other methods you know for finding limit of a function? Okay, I will explain you the methods. Let's discuss a case where limit doesn't exist in one variable as well as two variables. See this example. See this example. fx is given by x if x is less than 1 and 2x plus 1 if x is greater than equal to 1. So what is the limit of this function as x tends to 1? What is the limit of this function? Left hand limit, if you solve, you get left hand limit means x less than 1. You use fx equal to x, you get 1. And right hand limit, For right-hand limit fx is 2x plus 1, so you get 3. Geometrically also you can understand it. It is x for x less than 1, means up to 1 it goes like this. Okay, here it is empty. Corresponding to 1, which point you have 3? 1, 2, 3. So the graph starts from here. 2x plus 1. It goes like this. So what is happening? As x tends to 1 minus, means from the left hand side, the graph of the function hits at this point, means at 1. So left hand limit is 1. But as x moves to 1 from the right hand side, the graph hits at the point 3. The left hand limit and right hand limit are different. That's why limit of this function does not exist. Now see an example of a function of two variables where limit does not exist. This is important for you. How to prove limit of a function of two variable does not exist. Left hand limit and right hand limit are same, means both limits are same in this case. Only then limit exists. Here the limits are not same, limit doesn't exist. Okay. In this case, xy can approach to 0, 0 in this particular example in how many ways? Infinitely many ways. So along each path, answer of this limit or value of this limit should be same. If the limit exists along any path, I approach to 0, 0 along each path, limit answer of this limit should be same, means limit should be path independent in case it exists. But suppose along to different paths you get different answers, that means the limit does not exist. So here the problem is show that this limit does not exist. It means you have to find or think two suitable paths, at least two suitable paths, along which you have different answers of the limit. So let me choose first y equal to x. Y equal to x is the straight line. Along this path, let's see what is the value of this limit. When y equal to x, then the limit goes to only one variable x. X into x means x square plus x square. What do you get? 1 by 2. Okay, next path, let me choose y equal to 2x. 2x means another line through the origin. What do I get along this path? X into 2x over x square plus 4x square, 2x whole square. I'm solving the same thing again along this path. So what do I get? 2 over 5? 2 over 5. You see, along the two different paths, you have different answers for the limit. What does it mean? This limit does not exist. If you are able to show the limit is path dependent, along different paths you have different answers, the limit does not exist. Okay, in this case there are only two paths, so you have found limit along the two paths and you are saying that limits are different, so limit does not exist. Geometrically, you can say here limit doesn't exist means the graph doesn't strike at the same point. From left side, the point of strike is different. From right side, the point is different. Here, what can you say? If limit exists and limit doesn't exist, this could be interesting. Here, the plot is a surface. Okay, plot of the surface is shown in the lecture notes. You will see that the surface is rumpled at this particular point. Okay, let me give you one proper example of the geometry that will help you to understand, especially when limit exists. See this example of one variable. Limit of the answer of this limit is 1. Geometrically, it is semicircle. So as x goes to 0 from the left, it strikes at this point, which is 1. And as x goes to 0 from the right hand side, the corresponding curve strikes again at 1. So it is fine. See a similar example in case of two variables, where the limit exists. And answer of this limit is again 1. But see the geometry. This will give you an idea what happens case of two variables when limit exists. You know, the graph of this function is a hemisphere. Domain of this function is this unit circular disk. So at 0, 0, what is the value of this function? This, the topmost point, z equal to 1, or you can say 0, 0, 1. Okay. So what happens as xy approaches to 0, 0, say along this path. So there is a corresponding curve on the surface that goes to this point. This side, if you consider a curve path approaching to 0, 0, the corresponding values of the function move along the surface and go to this point. So whatever path you consider in the domain along which xy goes to 0, 0, the corresponding curve on the surface goes to this point. So you see what's happening? From all directions, the surface is converging to this point. In this case, there are only two directions. The curve is approaching to the same point. Here, the surface is approaching from all directions to the same point. That's the meaning the limit exists. If limit doesn't exist, then what would happen? Under certain direction, it is going down, and some other direction, it is going up. It is ruptured. There is some kind of, you can say, dip at that point. Lesser height on one side, greater height on the other side. It's like that. So hope you understand geometrically what happens when limit exists and what happens when limit does not exist. Okay, now let's go to the methods for solving the limit. One method you have learned, that epsilon delta approach. Let's see another method. It doesn't work for all the problems, but some particular problems can be solved. Sandwich theorem. Do you recall in case of function of one variable? If there are three functions, fx, gx, hx, satisfying this inequality in the neighborhood of x0, and limit x0, limit x going to x0, gx is L, and limit of hx is also L as x goes to x0. So if these conditions are satisfied, what can you say about the limit of fx? Limit of fx is also L. This is sandwich theorem. Geometrically, actually these are three curves in xy plane. Goes like this. Say there is another curve. This is your gx, bottommost, uppermost hx. At x naught in particular, what happens? The curves become closer because fx is lying in between the two. So naturally, limit of fx has to be L as x tends to x0 because gx and hx are having the same limit at this point. Gx and hx curve hit the same point, and fx is lying between the two, so it will also hit the same point as x tends to x0. That's why this result works. Same result you can write for a function of two variables. But now geometrically these are different things. Now instead of curves, these are surfaces. Okay, there are three surfaces. So suppose limit of gxy as xy goes to x0, y0 is L. And same is the limit for hxy as xy goes to x0, y0. So if these two conditions are satisfied, you can say that limit of fxy is also L as xy goes to 0, x0, y0. So it's a similar result, okay? Now let's see some problems. First see this side. If I ask you find the limit of the function x sine 1 over x as x goes to 0. So how to do this? Using sandwich theorem. You know sine 1 over x lies between, whatever is x, lies between -1 to 1. It lies in this interval, always. Of course, x is non-zero here because x tending to 0 means when you have not taken the limit, x is non-zero. So it is a well-defined quantity. In any case, it lies between -1 and 1. Okay. Multiply both sides by x. Multiply the inequality throughout by x. If x is positive, it's fine. Otherwise, you can write the inequality in reverse order if x is negative. In any case, limit of this function is clearly 0. This also 0. This is the middle function, so its limit should also be 0. This way you can apply sandwich theorem. See a similar example for a function of two variables. xy going to 0, 0. Y times sine 1 over xy. Suppose you are given this problem. Find the limit of this function. So if you are able to think the inequality of this kind means you can write this like this. Y is less than equal to y sine 1 over xy less than equal to y. Sorry, minus y this side because it lies between -1 and 1. So you multiply it throughout by y. For y positive, y is negative, then you can reverse the inequality. Okay. So if you apply the limit for this function as xy goes to 0, 0, means y goes to 0, it is 0, this is also 0. So you, by sandwich theorem, limit of this function is also 0. Okay, so the main difficulty that may be here while applying sandwich theorem is that you have to set up this kind of inequality where you know the limit of the extreme functions and that limit should be same. After that, you can write limit of the middle function. Okay, so hope you understand the sandwich theorem. Now let me discuss one more problem, a different method for finding the limit. That is using epsilon delta, but there is some difference in this example. You will notice that. Suppose you are given that prove that limit of 4x square y over x square plus y square is 0 as xy goes to 0, 0. So limit is given to you. You have to prove this limit. If you directly substitute, there is a problem, okay? You cannot do that. So how to do this? Using epsilon delta. In epsilon delta, what you need to start with? You have to prove that this is less than epsilon. This is less than epsilon in some neighborhood of the point. Let me choose square neighborhood, circular neighborhood. Okay, I can choose square neighborhood also. Given epsilon positive, there exists some delta positive such that for all xy in this neighborhood, mod fxy minus L is less than epsilon. You know that definition. So we have to establish such a condition to prove this limit 0. Let's see. Here fxy is 4x square y over x square plus y square minus L. L is 0 here. Now establishing such a condition directly is not looking feasible. Okay. So see what I do to get such a condition. Put x equal to r cos theta means use polar coordinates and y equal to r sin theta. What do I get? 4 times r cube x square means r square cos square theta and r sin theta, so r cube and sin theta as well, divided by r square, right? Because x square plus y square is r square. So you are left with 4 times, or you can write r outside if you like, 4 times r modulus of cos square theta sin theta. Now cos theta sin theta you know are less than equal to 1. Modulus of the whole thing is less than equal to 1, so you can write it less than equal to 4 times r. But what is r? Square root of x square plus y square. You want this thing less than epsilon. This can be less than epsilon for mod x square plus y square less than epsilon by 4. Correct? This you can choose your delta. You have got neighborhood of 0, 0. You see this whole thing is neighborhood of 0, 0. You can write x minus 0 whole square, y minus 0 whole square. So you have found a neighborhood, delta neighborhood of 0, 0 for which mod fxy minus L is less than epsilon. So limit of this function is 0. So you see the manipulation for getting this condition, you have used polar coordinates. So this could be another trick in some problems. Okay. So hope you have understood whatever I have explained, mainly what I have done in this lecture. I have explained you the concept of function in 1 variable, 2 variable, 3 variables, along with the geometry, explaining what is the difference between the different cases. When the variable increases means when the function goes from one variable to another variable, then how the geometry changes, domain changes. Then I've explained you the concept of neighborhood. Very important. As you see, neighborhood is used everywhere when you are doing the problems on limits. After that, I've told you interior point, exterior point, boundary point. Those are simple things, you understand. Then the main concept that I've explained is of limit. Meaning of limit, epsilon delta definition, geometrical meaning, when the limit exists, when the limit doesn't exist. So you should look at all those counter examples given in this lecture, okay? So after listening all this and thinking carefully, I'm sure you will understand these things very, very clearly. And not only this, this will generate your interest in learning the higher order calculus. And I tell you, calculus lies at the heart of mathematics. If you learn calculus carefully, you will enjoy different disciplines that come out of mathematics. So the contents delivered in this lecture are very, very important, very, very elementary for all of you. Okay, so thank you. We will meet in the next lecture. There I will explain the concepts of continuity, then differentiability. You will see that those are also very interesting. So that those things we will do in the next lecture.